Hey gang, and welcome to another worksheet solutions walkthrough for the worksheet reaction and mechanism practice with carboxylic acids. Okay gang, this is the only practice on jOeCHEM for carboxylic acids. I don't want to say it's a short unit, but a lot of functionality comes afterwards in the next unit where we talk about the carboxylic acid derivatives. But there's still some work to do here as well. That's why you're here. So you know the drill. You've seen the worksheet, you've seen the associated videos, you did some practice, you're a little confused about the answers, but you're in the right place. I'm going to show you how I arrived at all the answers. I'm going to uncover and hopefully deshroud any confusion, mystery as to how those answers were arrived at. So let's get started. Okay, gang, rolling on into problem one. This is going to be part one of two. I'm going to do the first three, then I'm going to do the second four in part one, okay? So if we take a look at this lovely first problem up here, I presented this to save space for myself on the worksheet, but also, I feel like some people will present, functional groups in ways that maybe you're not used to seeing them. So, this is an aldehyde, and we can absolutely draw that like this, right? Don't think just because, it's CHO, just be aware. So I personally would redraw this. It's totally up to you how you want to handle it. But in this two-stepper that we see here, right, we'll take the problem one step at a time. This first step is going to be cyanohydrin formation, right? Remember, just because we went through all that carbonyl and ketone stuff then doesn't mean it can't keep coming back up, and it does seem to come back up very frequently. So after the first step, right, what this turns into, and remember, it's this carbon here that will turn into the cyanohydrin, right? We have an OH, and I'm going to ignore stereochemistry. Don't worry about stereochemistry. That's the cyanohydrin, but then we see this second step of acid and water. And remember what happens when we hydrate nitriles, right? Nitrile being a CN. They turn into carboxylic acids. So this will then turn into a carboxylic acid. So our product over here, we get the OH that resulted from the cyanohydrin formation, but then we're going to have one more carbon over here. It's this one right here, and I'm not going to explicitly draw it out, but then that turns into a carboxylic acid, and that is how we get our first product for the first problem in problem one, okay? Now, this one down here, the second one, it's a fill in the reagent type situation. So you can see we have an aldehyde completely unaffected in both scenarios, and then what we have here, what starts out as a, tertiary alkyl chloride turns into an addition, an extension of the carbon chain with a carboxylic acid seemingly appearing out of nowhere. And remember, in this carboxylic acid unit, we did Grignard reactions with CO2, and then with a subsequent protonation, we got carboxylic acid. So we do know how to extend our chain. The trick here in doing that, because that is what we have to do, the trick is, how do we make sure that the aldehyde doesn't get caught in the Grignard crossfire? And again, coming in, hailing from the carbonyl like ketone aldehyde unit, we can protect, right? We can use an acetal to protect and then deprotect. So what I think we should do first is add that protecting group. So let me make sure I'm using exactly what I have on the solution sheet. So I used this ethylene glycol. Remember, so you need an acidic environment. Throw in a diol of your choice or whatever you like to protect with. Ethylene glycol is a standard that I've seen over and over again, so that's what I'm using. That's why I'm using it here. So remember, what that will do is right off the bat, we will have this, okay? Completely protected. It's acid sensitive, but don't worry. We won't run into acidic conditions until we're protonating after the Grignard reaction, which will give us more bang for our buck anyways. So we're going to protect in the first step, and then what we can do is then we can create our Grignard reagent. Remember, it doesn't matter that I have chlorine here. Chlorine, bromine, doesn't matter, right? So this is after step one. I'm going to cheat and say after step two, what we have is MgCl, right? And what we've then done really is make this carbon nucleophilic. Remember, this has a lone pair now. And then what we'll do is then we throw in, as we roll into step three, CO2, because what will happen then, remember, is our Grignard, right? That's a really partially positive carbon being double bonded to two different oxygens. This carbon attacks, that double bond functions as a leaving group, that gives us a carboxylate, right? So then the last thing we need to do here, let me kind of circle this as our answer as well, is we're going to need H3O plus at the end, but remember what that will also do. Not only does that quench the negative charge that ends up on this O minus, that will unravel the acetal because we're putting in, it's acidic conditions, but we're pumping water back in, right? So if you want to think about it, this could be H3O plus, or you could have H2O comma H plus. Up to you. Either way, it's important just to understand, not only will step 4 quench the negative charge after the Grignard reaction, it will unravel the acetal, deprotect, and give us the aldehyde back completely unscathed from the Grignard that we use to attack CO2 and lengthen the chain by 1. Okay? Erase this, make some room. And to round out the first part of this two-parter, we have benzoic acid right here. And so the first step, these two, right? What this means to us is, remember, carboxylic acids, we can't reduce them with just NaBH4 and ethanol. We need a more aggressive source of H minus, of hydride, right? We get that with lithium aluminum hydride, and then with the subsequent protonation workup, right? So all this does, after step 1 and 2, we're just gonna have an alcohol on the benzoic carbon. The carbonyl gets wiped away, and then what we have here, right, and again, that me drawing that carboxylic acid like that was for convenience, but also to give you a different look at the functional group. What we have here is catalytic H2SO4, a carboxylic acid, and an alcohol. So we're going to be creating an ester, right? This is ester formation, right? And that goes through an additional elimination mechanism, right? We know this gets protonated first. That activates the carbonyl carbon. The OH attacks there, and then we get kicked up, kicked back down, right? I can even draw the arrows in a makeshift way, up, down, right? This would be protonated. That gets booted off. I know that was really janky in a way, but that's all to say what we get is, just know this carbon that I'm starring right there is that carbon right there. That's where we'll have our carbonyl, right? And then the next, we will bond to this oxygen right here. That's important to note. It's this oxygen right here. Then we have the extra carbon and then the benzene ring. Carbon, benzene ring. So, kind of an interesting problem where I kind of wanted to flash you a carboxylic acid, but then, be like, just kidding. We're going to turn it into an alcohol, and then we're going to take that alcohol and I'm going to introduce a different carboxylic acid, and then we're going to make an ester that way, right? And I'm just going to make sure I didn't lose any carbons. There's one carbon off there. Yeah, okay, that looks good. Okay, gang, that is the first part of problem 1. We have 4 more. Complete the reaction, provide the reactants, fill in the reagents type problems. But let's keep going. Okay, gang, for part 2 of problem 1, we have 4 more lovely problems. And in this first one, we actually have to provide the reactants, and we see we have this result, like this product over on the right. So what you're seeing is obviously acidic conditions, right? That's what we get from seeing the H2SO4. And if we look over here, in terms of what functional group we're looking at, remember, this is an acid anhydride, right? And you can see that because we have carbonyl, oxygen, carbonyl, right? That's what's characteristic of an acid anhydride. Now, what we're basically seeing is the formed acid anhydride product, and we need to step it back to what 2 carboxylic acids created this. And or we could just say what 2 structures, and we know that we get this when we smush 2 carboxylic acids together, because in terms of one carboxylic acid and the other, one OH functions as the leaving group, and the other, if this is what leaves, then this oxygen is the glue that sticks them together, the whole, the 2 pieces. So when we take a look at this, what you need to do is just essentially realize that one piece, and it doesn't matter if you cut it like this, that's going to be a carboxylic acid, and this will be a carboxylic acid. Both sides are a carboxylic acid, right? I guess more appropriately, I should draw this right down the middle, like right there. So what you should come up with is 1, 2, in terms of a 2-carbon carboxylic acid right there. That would be the left piece. Over here, it's a little bit weirder. 1, 2, 3, 4, 5. I'm a little constricted on space. Then a carbon up. I'm going to move the plus over here, actually. So carbon up here. So these 2 carboxylic acids would add together to form the acid anhydride we see over on the right. Okay. Now, down here, with a lot of steps, but we're just going to take it one step at a time, and we'll be at the product in no time. I will use this space over here to kind of do my work because not enough space over here. So in this first step, right, we see we have an alkene, a double bond. And yes, this is a blast to OCHEM 1 pass, but I want to try and bring these things up from time to time to keep you all sharp. So this is a Markovnikov addition of HBr, but it's an anti-addition, remember? And this only works with HBr. Actually, I'm going to start down and work my way up. So remember, after this addition, the anti-product would go right here on that carbon. So we get a bromine right there. And then I'm actually going to cheat. I'm going to combine step 2 down here because we have a primary alkyl bromide. We then toss in magnesium. So what we get after that is MgBr. And then we do an ingredient attack on CO2. So remember, right, you have carbon dioxide like this. You attack, blah, blah, blah. And in terms of like double bond, getting functioning as our leaving group. So remember, we're gonna have one additional carbon off of now this dot carbon. So after step 3 and 4, I'll combine them together because that protonates us up to, so it's this carbon. Now this is the carbon that was the CO2 carbon. That is after step 3, but then step 4 protonates and quenches the negative charge on that oxygen. And then step 5. So basically that was a whole bunch of craziness just to get a carboxylic acid, and then we toss in an amine, right? Now we're going to make an amide, right? Because carboxylic acid plus amine equals amide, okay? So the product here, you still have the carbonyl, the C double bonded to the oxygen, but instead of this now, we're replacing it with that nitrogen piece right here. And remember, it will lose, so we have to lose this H so that nitrogen can have a neutral, a zero formal charge and be neutral. But that is what we will get. You can see that's an ethyl piece, that's an ethyl piece, and there is our amide right there. Okay? I'll erase this because I need the space back. Whoops. Box this up here too. Okay, so over here, what do we have going on? So we see an alkyne. Haven't seen them in a while. Well, in this first step, I hope you see boron and you remember, you hear a little voice in the back of your head whispering anti-addition as well, right? So remember, we're going to hydrate this triple bond, right? We see boron and peroxide, specifically hydrogen peroxide. So what we get after step 1 here, I'll do this over here. 1, 2, 3, 4. We have 4 carbons, but remember, we're doing an addition of water. It'll be in the anti-position, the lesser substituted carbon. And remember, we get that tautomerization. We're going to get a carbonyl, right? Seemingly out of nowhere, but it's because we add water there. There's going to be a double bond left over. It's an enol. We know enols. They're good friends of ours by now. We then tautomer to a carbonyl. Here's an aldehyde. Okay? Second step, we're going to oxidize it up to a carboxylic acid. Oh my gosh, I don't know. Somehow chunking up the pronunciation, my brain just kind of short-circuited. Okay, and then last but not least, step 3. Remember, all PBr3 or SOCl2 does is replace the OH of a carboxylic acid with the corresponding halogen. So our product here is actually just the 4 carbons, and it's an acid bromide. That is where we stop here in this problem, okay? Now, last but not least, what do we have going on down here? Again, we see an anti-addition of water, an anti-Markovnikov addition of water. Here, we're doing it on an alkene, though. So what you can see, and I'm going to do a little work over here, is after step number 1, we're just going to have a primary alcohol. But not for long, because step 2 actually shows us oxidizing it all the way up to a carboxylic acid. So step 2, that primary alcohol becomes a carboxylic acid. Note, we still have just 1 carbon outside of the 6-membered ring, okay? And then these 2 steps together. Remember the HVZ reaction, and I always forget the full name. Voldhart-Zelinsky, I believe, HVZ. That will help us brominate on the alpha carbon to the carboxylic acid. Now, the one condition is you need one hydrogen, 1 proton there. We do have it. So for steps 3 and 4, which end up being our product, so I'll just we're going to put a bromine on this carbon, replacing a hydrogen. There has to be at least 1. So our product here bromine right there. And that rounds it out for problem 1. Let me just make sure I didn't make any. Okay. Yes. So, deconstruction of an acid anhydride, amide formation after a wild goose chase, formation of an acid bromide after some trickery and some old OCHEM 1, more OCHEM 1, and the HVZ reaction. Okay, gang, that does it for problem 1. We're going to do problem 2 and those, more pointed mechanisms like the ester formation, the amide formation, the acid anhydride, the acid chloride. I'm not going to go over those in the walkthrough. Those are for your own practice, so just compare them against the solutions. That's my long way of saying we're done with problem 1. We just got problem 2 left, so stick with me. We're almost done with this walkthrough. Okay, gang, so as we step into problem 2, if we take a look at part A, I'm going to do A, and then I'm going to pause video, erase, and then do B, because I'm going to need some space. So up here, we are tasked with ranking these 3 in terms of, their relative acidity to one another. 1 being the least acidic. Whoa, what am I doing here? 3 being the most. Okay? So, they're all carboxylic acids. We know that, right? So there are obviously some visible small differences, and we just need to make sense of what what they are and how they affect the relative acidities of these 3 carboxylic acids. So, if we take a look here, right, we all see that there are 2 carbons, but this one is 3 carbons. So, noted. And the other thing we see is this group right here, this sulfonyl group. Remember, we ran into those when we did benzene and specifically, right, like electrophilic aromatic substitution reactions with benzene. We know they're very strong electron withdrawing groups, right? So what we really have here, I'm going to, I don't think you need to be able to expand this to get this problem correct, but that's what we really have. Don't forget your acid-base basics. Remember the inductive effect, okay? So what we have here are 3 oxygens. And yes, they are taking and stealing sulfur's electron density heavily because they're more electronegative than sulfur, but they're probably pulling a little bit harder than just on sulfur, right? We can, show some dipole arrow that's saying not only is sulfur super partially positive, but probably this carbon, and to maybe even a small extent, this carbon's feeling that effect. Remember, the inductive effect. These are super, super, super electronegative. There are 3 of them. They are pulling and they are greedy and they want electrons. So this is going to be a positive force and increase the acidity of this carboxylic acid because remember, in every situation, we will be losing this proton and having a negative charge, and we are thinking about how, the differences between these molecules. What will make them happier in their conjugate base state? Because if they're happier, that means they're weak and stable, which means they came from a stronger acid. So in terms of all 3 of these, no one has a group that is, providing this type of positive inductive effect, right? Because if electron density is moving this way, that means there's more partial positivity over here, which is going to help stabilize this oxygen that takes on the minus charge. So this by far is the most, it's very easy to see because of the sulfonyl group. This is, like we do it in red, this is the most acidic, okay? Now, let's look at these 2 because they're very similar, but there's a slight difference that makes the difference. So we see there's an extra methyl group over here. Now, again, I'm going to harken back, and it just so happens that this is applicable to, the EAS stuff. Remember, in our EAS travels, we saw alkyl groups. They were plain, but they were slight activators of the benzene ring because they lent electron density through hyperconjugation. Well, because the presence of this methyl group through a smidge of hyperconjugation provides an extra slight negative presence through hyperconjugation, well, there's a negative charge there in the conjugate base. So the methyl group actually does exactly with the opposite of what the sulfonyl group does. It kind of makes that negative charge slightly uneasy. It doesn't exist over here. So this carboxylic acid is more acidic than this one over here, which is the least acidic. Whew. Okay, gang. I'm gonna wipe this up, and we're going to do a mechanism that I think is pretty cool because, yet again, we're reaching back into our knowledge of, ketones and aldehydes and pairing it with this new knowledge of carboxylic acids. Okay, gang, rounding out problem 2, as well as the whole worksheet solutions walkthrough, we have a mechanism problem. We need to show the arrow pushing mechanism as to how this structure proceeds to this in, catalytic H2SO4 and water. Now, if you're groaning, thinking, Joe, really? another ring expansion problem. I thought that was over with. I thought that was jOeCHEM 1. I thought we were done. Well, no. But I think you might find this cool. And it's more combining of your aldehyde ketone knowledge and your carboxylic acid knowledge. And what more could you ask for? So in this problem right here, what is actually key is being able to pick out what's in the reactant and in the product. And you'll see what I mean. Because it does look, we have a lot of similarity, right? We have a cyclic, we have an oxygen embedded in our ring here. We have an oxygen embedded in our ring over there. But think about what we have over here. We have a carboxylic acid, and and it's been a while, but this is a hemiacetal, right? It's not a full-on acetal where we have OR, but we have OR and an OH, which is, this was once a carbonyl, oxygen up top, okay? Now in our product, no hemiacetal, no carboxylic acid, but what we have is an ester, and more specifically, what people in the biz would call a cyclic ester. It's more specifically a lactone, right? A lactone is just a cyclic ester, okay? And we have an aldehyde, okay? So follow me on this. And if you didn't get this at first, you don't have to see it at first. But with the H2SO4 and the H2O, I think what we're going to do first is this hemiacetal. We're going to unravel it and recover the carbonyl it came from, as well as the alcohol that attacked it. Then that alcohol, once free, is going to attack the carboxylic acid when, that will be prepped for ester formation because we're an acid. And then we will produce the cyclic ester. And I guarantee the rings will work out. The ring count will work out, okay? So even if you didn't see that, hopefully the thing you might need to see at first, though, is that you see a hemiacetal, you see H2SO4 in water. So the first thing that's going to happen is we're going to protonate we're going to work with the hemiacetal to unravel it, okay? So what's going to happen first, and I'm going to cheat a little bit to save some space, but I'm going to draw H2SO4, and what we need to protonate first is actually the oxygen embedded in the ring, because we need to reform this carbonyl by swinging these electrons down, and we can't do that until this is a good leaving group. So we're protonating this first to create a good leaving group. So the carboxylic acid is just waiting until it gets the nod to be involved. So we have here, plus charge on that oxygen right there. Didn't touch the OH up there, but now we will. What this is going to happen, what's going to happen now is this is now a good leaving group. We swing down electrons, we reform our carbonyl, and in doing so, we need to boot a good leaving group, and now we have that since we've protonated the oxygen that's embedded in the ring. So in doing so, we're unraveling I'm going to draw a line here so we don't get mixed up with the problem up here. We're unraveling the hemiacetal. So carboxylic acid still just waiting oh so patiently. So now what we have up here is an aldehyde, okay? So I kind of drew it's a short aldehyde. And then just one carbon and then an OH, okay? And what I forgot to draw is that aldehyde still has a positive charge because that hydrogen is still present on it. So now that we've unraveled the hemiacetal, what we need to do is actually a little bit of a proton shuffle. This aldehyde is this aldehyde in our product. And this carboxylic acid is not yet ready to be attacked to do ester formation. So what we need to do is deprotonate this and protonate this to make our carbonyl carbon more reactive, right? Put a stronger partial positive charge on it. So, and if your proton shuffle is a little rusty, break it back out because we are going to deprotonate the aldehyde. And we're going to protonate the carbonyl oxygen in the carboxylic acid, right? So if you want to, you can even toss a plus H plus minus H plus step up. You don't have to put that there, but just for old time's sake if you want to, okay? So now we have this down here. We have a plus charge on the carbonyl oxygen in the carboxylic acid. We just have a plain old aldehyde up here, okay? And then I have this OH here. So what's going to happen is this alcohol is super interested in attacking intramolecularly, right? And would you look at that? Look how far they're spaced out. A perfect 6 to form the ring that we need. So this oxygen takes its electron pair, comes around, attacks the carbonyl carbon, and electrons kick up onto the OH and begins the first part of our addition-elimination mechanism, okay? So what's going to happen here? I know I'm forming a 6-membered ring. So let me just draw it. Let me number internally. And then I'll play who is attached to who. That's an ugly 5. Sorry about that. Ignore that. So on 1, we actually have 2 OHs, okay? And that won't stay that way, but at least that's the way it is for now. Nothing on 2, nothing on 3, and on 4, now you can see that we have, whoa, the aldehyde that we see in our product, 2 carbons out of the ring, okay? And then, last but not least, what I actually need to do is make sure in 6, that's not a carbon, that's an oxygen with a hydrogen and a plus charge. Okay, so we need to actually carry out this addition elimination mechanism to finish off the problem. So I'm going to cheat a little bit. I could absolutely do what I did with the H2SO4. Actually, I'll make sure to do that. So just, again, we need to prepare a good leaving group. And we're going to kick off this, it doesn't have to be, we just have to kick off one of these 2 OHs and reform our carbonyl to get the ester. And we're going to deprotonate this to keep this around. So in this step, we're prepping one of the OHs to be a good leaving group. And I'm going to actually deprotonate this oxygen right here to make it a worse leaving group so that it sticks around and the mechanism doesn't go backwards, okay? So I'm going to try and fit this all in. So we got OH, OH2+, and what happens here, so we've done the addition, and now comes the elimination part of our addition elimination. Electrons swing down, we reform the carbonyl carbon, we boot off OH, or like water, OH2+, and we finally get our lovely product, the lactone, with the aldehyde on the bottom, using all the board space. Okay, gang. So, like I said, this is it for carboxylic acids. Feel free to do the 4, what I would say more straightforward problems for practice, right? You need to be really good at these addition elimination mechanisms. It's good practice. Didn't feel like it needed to be part of the walkthrough because these things are already, they get long as is. And you can check the solutions for anything you might need if you run into issues. That does it for this worksheet. Whew, gang. If you're watching this, first of all, that means you probably have watched a lot of jOeCHEM videos, so thanks for being a trooper and hanging in there, and and for taking OCHEM in general. But thank you for watching jOeCHEM. No one has to watch these videos, and this video in particular, if you're watching, that means you've paid me some money, so thank you for that. You don't have to do that at all. I'm so glad you're using jOeCHEM. I really hope it's helping you understand OCHEM, and as a bonus, I hope you like it as much as I do, because it's cool, man. It's cool, gang. But thank you for watching. If you're watching right now, I hope you're using jOeCHEM to the end of your organic career. And no matter what, I hope to see you all in the next video.